Hello and welcome to another lecture for my class, PSYC 440/640, the class that, as you know by now, is called Experimental Methods, but is really a class about univariate data analytic techniques from a model comparisons perspective. Anyway, as usual, I'm beginning with a comic from the webcomic series PhDcomics.com, describing humorously, I suppose, a situation that most people can relate to if you are in graduate school or have ever been in graduate school or just in academia. So enjoy the humor if you can. Sometimes it helps to laugh to keep from crying. And if you're enrolled in my class, or if you're just, I guess, watching this video on YouTube and you want to play along with me, start SPSS on your computer now. Today's lecture is going to be called More About Interactive Models, not a very creative title, but as you can see here, I'm going to focus on moderation, that is, working with models in which there is an interaction term that talks about or refers to two or more of the predictor variables. So as is often the case, we'll begin with a quick review and then I'll move on to talking about moderation. Particularly how we kind of understand or how we can characterize moderation or interaction in our model when it occurs. So here's the review, kind of where we left off last time. We're imagining that you're a clinical psychologist, you're studying eating disorders, and you have two predictor variables in your model. One is a measure of self-esteem, the other is a measure of negative body image, and you're allowing that these terms are going to interact, which is to say you're making an interaction term in the regression module of SPSS, or you could really do the same thing in Excel, it's not that hard. And then you're using these predictors, self-esteem, negative body image, and their interaction to predict an outcome variable, which is a measure of eating disorder symptoms. Now, if you're enrolled in my class and you have access to Blackboard, you can get this data set online pretty easily. If you're not enrolled in my class, and if you're really patient, you can copy the data off this image here. Just pause the video. You can see we have 60 cases. I had to divide up the columns so as to make them fit properly on this slide. For each person, we have eating disorder symptoms, that's EDS, self-esteem, that's SEL, and negative body image, NBI. Right there. So again, if you're really dedicated to learning this stuff and you're not enrolled in my class, pause the video right now, carefully copy all these numbers into SPSS's data frame or into Excel's spreadsheet, and you can more or less play along with me and with the rest of the class as we go. Anyway, as we sometimes do, we want to represent these variables pictographically. So here is our predictor variables, or here are our predictor variables, and here's our outcome variable. And we're kind of looking at the relationship that exists between these sets of variables. Now, last time, the way I presented this is as an example of an opportunity to use hierarchical multiple regression, or sometimes called sequential multiple regression. So in step one, we're entering our main predictor variables, self-esteem and negative body image. And in step two, those predictor variables stay in the model and the interaction term enters. And this allows us to kind of test a hypothesis about whether the interaction of those two predictor variables significantly improves the fit of the model to the data, like essentially allowing what would otherwise be a flat plane describing the relationship between self-esteem, negative body image, and eating disorder symptoms, allowing that flat plane to warp or kind of wobble a little in space, if you like to think geographically, or geometrically, I should say, to see whether that improves the fit of the model to the data. And it turned out that it did, and that's no big surprise because this is fake data that I cooked up to illustrate the example, although I should say it is based, at least loosely, on real research that is done in the area of eating disorders, which I know of because my wife is an eating disorder researcher, among her other skills. Anyway, you can see here we have in SPSS our two models. Really two augmented models. The first augmented model includes just negative body image and self-esteem. That's model 1, what SPSS calls model 1. You can see that that model is statistically significant if you look at the ANOVA table. So a comparison of that augmented model to a compact model that has no predictor variables is statistically significant. And then you can see that model number 2, that's the augmented model that includes the interaction of our two predictor variables is also statistically significant if you look at that ANOVA table. And what's probably even more interesting or more important to notice is that if you look up at the model summary and you move your eyes all the way to the far right, you can see that there is a significant change in R squared when we go from augmented model version 1, if you will, to augmented model version 2. So we get an improvement of about 3% of the variance explained, if we want to be kind of generous. So R squared for model number 1, augmented model number 1, explains about 63% of the variance. R squared model 2, we are explaining about 66% of the variance. Obviously, that's a difference of 3%. That difference, although small, is not so small as to be not statistically significant. That is, it's not so small as to be kind of indistinguishable from 0. So we have a significant change in R squared, and that's good. That's maybe telling us something. Sliding down our output, we can see here that the interaction term itself, if we evaluate it in terms of its coefficient, it significantly predicts the outcome variable, that is, eating disorder symptoms. And if we also keep on going down in our output, we can see this little table here called excluded variables. This is just telling us that at step 1 or at model 1, before the interaction term had entered the model, that's at step 2 or in model 2, SPSS kind of wanted to add it in. It was at that stage an excluded variable, the interaction term was, but SPSS does like a little significance test and says, well, you know, if you added it in, it would make a significant contribution to the model. You know, you probably don't need to look at this table because, of course, you decided to add in the interaction term. That was a decision you made as the researcher, but SPSS gives you this little bit of output as well. You'll also notice that includes some collinearity diagnostics here. We see that the variance inflation factor, VIF, is rather high for this interaction term, and its tolerance is rather low. Under other circumstances, this might bother us or concern us a little bit because it suggests that this interaction term is highly correlated with the other predictor variables, but that shouldn't really surprise us, of course, because it's made of those predictor variables. We make the interaction term by computing the product of our two predictor variables, so of course it's going to be correlated. And in fact, there's a way that I've hinted at before to reduce multicollinearity problems when interaction terms are present, and I'll get to that a little bit later, either in this lecture or in the next one, I forget. So anyway, in this case, including the interaction term fits or improved the fit of the model to the data, but it was really done just kind of for the purposes of illustrating an example for fun, you might say, if you consider this stuff sort of a fun thing to do. I want to be clear, though, that when you're doing real research, including an interaction term in a model is a decision that you really should make based on a good reason. Now, especially this is the case when we're working in the regression module of SPSS, where SPSS will not make for you interaction terms and or will not include for you interaction terms in your model unless you make them and you add them in. That's a little bit different than when we're working in the ANOVA module of SPSS or the general linear model, GLM module of SPSS. There, SPSS tends to want to make interaction terms or between all of the predictor variables that you give it. And why that is probably just has a lot to do with sort of the history and the traditions of ANOVA type research as compared to regression type research. But the important idea, whether we're working in a regression module or ANOVA module or GLM module, is that you should be kind of thoughtful about whether or not you want to have an interaction term in your model. You should ideally make make the decision to include one if you have a particular prediction, a particular research hypothesis that you're trying to test. And that research hypothesis probably goes a little something like this, that the relationship between one predictor variable and the outcome variable depends, at least to some extent, on the other predictor variable. So the relationship between negative body image and eating disorder symptoms is not constant across all levels of self-esteem. It kind of depends on if you have high self-esteem or low self-esteem. Perhaps that's a bit vaguely put, but that's the essence of a research question, or maybe more precisely, I guess, stated as a research hypothesis, that there is some moderating effect of self-esteem on the relationship between negative body image and eating disorder symptoms. That would be a specific claim or hypothesis that you could test by including an interaction of those two predictor variables in your model. again, if you wanted to represent this pictographically, you might use the following convention. You're trying to represent the relationship between negative body image and eating disorder symptoms that is moderated or influenced in some way by self-esteem. Now, you may at this point ask, well, which of our two predictor variables is the main predictor variable, if you want to call it that, and which is the moderator? It really depends on your hypothesis. There's no reason why you couldn't sort of flip these variables around and say, well, self-esteem has some relationship with eating disorder symptoms, and that relationship is moderated by negative body image. How you frame this depends a lot on the specific theory that you have about these variables and the specific hypothesis or hypotheses that you're trying to test about them. So now I'm not an eating disorder researcher, but having read some of that literature and having talked to my wife about this over the years, here's my take on how you might frame a hypothesis in this type of example. A good hypothesis might be something like self-esteem moderates the relationship between negative body image and eating disorder symptoms, assuming there is such a theory to support that hypothesis. And in fact, I think there is. But so based on some theory, you make that claim, you make that hypothesis. It might be a little bit better though, or you might be more precise if you said something like, well, self-esteem moderates the relationship between negative body image and eating disorder symptoms such that this relationship is stronger among people with low self-esteem than among people with high self-esteem. That's essentially the same hypothesis, but I'm saying it's better because it's more precise. It kind of hints at or points towards the nature of that interaction. How does that interaction work, or how does it kind of play out? And I think where possible, it's good to make relatively precise hypotheses as compared to relatively vague hypotheses because, well, for all sorts of reasons that have to do with the philosophy of science and the statistics that we use and so on and so on. Precision is good. Precision is, generally speaking, desirable. Now, to be clear though, whichever way we set it up, the idea is the same. The effect of the one predictor variable on the only outcome variable is moderated or influenced by the other predictor variable. Now, in some cases, our moderator is a categorical variable. That is, it's a variable that can assume only discrete levels. A common categorical variable might be a gender, where people are either male or female, or maybe we have male or female and transgender, some sort of discrete groups that we put people into. In those cases, we can visualize often fairly easily with a graph like this one, how the relationship between our main, let's call it predictor variable, and our outcome variable changes or differs across levels of our moderator variable. So here we have a study, I actually forget the reference for this, but essentially we're looking at levels of job training. People get different levels of job training, and they have, of course, different levels of job performance. And you can see that job training generally improves people's job performance. To the extent that you have higher levels of training, you tend to do better. However, this effect, this relationship, is moderated to some extent by level of autonomy. And for the sake of visualization, there's some way, let's imagine, to divide people into highly autonomous folks and not very highly autonomous folks, low autonomy versus high autonomy. You can see that for people who have high autonomy, job training greatly increases their job performance, but for people with low autonomy, job training does not so greatly increase job performance. That would be a way to represent kind of with a pictographic aid, a graph in this case, a moderated relationship. And it gets, I think, it suggests the idea that we're talking about. Now, to summarize or to highlight some important points here, these following statements mean the same thing. The effect of one predictor variable depends on the level of another predictor variable. Another statement, the slope of one predictor variable depends on the level of the other predictor variable. Those are essentially the same thing, whether we're describing it in words using things like phrases like the effect of the variable, or if we're trying to describe it pictographically using a graph, we're literally seeing that the slope that describes the relationship of one predictor variable and the outcome variable, that slope changes. It's steeper or shallower at different levels of the other predictor variable. So when a significant interaction is in the model, it can actually become kind of difficult to discuss the simple effects or the main effects of any one predictor variable. In a sense, the main effect of a predictor variable is tied up with, or is dependent upon, or is moderated by, is contingent upon the level of the other predictor variable. That's the essence of the interaction. And I know I showed this picture in my last lecture. It comes from Andy Field's very good statistics textbook, Discovering Statistics Using SPSS, and it illustrates some, I think this is actually based on real research, the relationship between video game use and aggression, and whether or not that relationship is moderated by callous and unemotional traits, that is, personality variables that have to do with being rather callous and unfeeling towards others. Now on the left you can see a model that does not include an interaction. There is a relationship between video game use and aggression. Generally speaking, the more video games you play, the more aggressive you are. There's also a relationship between callousness and aggression. Generally speaking, the more callous you are, the more aggressive you are. But the relationship of one predictor variable and the outcome variable does not change at any level of the other predictor variable. So that slope that describes the relationship between callousness between video game use and aggression is the same slope whether you're at a low level of callousness or a high level of callousness. You can kind of see, I hope that those lines, those kind of purpley blue lines that represent the slopes across that plane, those are meant to be parallel with each other. Now on the right side of the screen you can see a model where an interaction term is included and that interaction is significant. Here, in a very real, to the extent that any math is real sense, the plane now warps. It kind of bends, as you can kind of see here, I suppose. And that bending is important because now it's not really possible to talk about the relationship between video game use and aggression in any sort of absolute or constant sense. If I say, if you ask me, what's the relationship between video game use and aggression, I would have to answer, well, it depends. If you're someone who's very low in callousness, very low in those personality traits, to the extent that you play more video games, there's maybe even a negative relationship with aggression. You become more chilled out and relaxed. However, as we become, as a person becomes more callous, or as we look to people who are increasingly more callous, we see a different type of relationship, such that when they play video games, the longer they play, the more aggressive they get. Or that's the nature of the relationship that's implied here in this graph. So the important point here, or an important point to kind of further elaborate on, is that we should really think about the different ways that the relationship between the predictor variable and an outcome variable could change across levels of the other predictor variable. And in an effort to illustrate this, I've cooked up some incredibly simple looking graphs here that I hope will be informative. Here's the first situation I could imagine. You have one outcome variable and a continuous predictor variable, and for the sake of easy visualization, a categorical predictor variable, which we're treating as a moderator. So here's a situation in which there's no effect of the predictor variable 1 or the predictor variable, aka moderator variable 2, on the outcome variable. To the extent that you have higher levels of x sub 1, you don't have any change or any different level of y, whatever the x sub 1 refers to. And likewise, to the extent that you are at level 2 of variable x sub 2 as compared to level 1, it doesn't really affect your level of the outcome variable y. Those lines really should be perfectly superimposed. I just kind of dragged them off of each other to help with the visualization. So here's a situation, pictographically represented, where you might say, well, there's no main effect of predictor variable x sub 1, and there's no main effect of predictor variable x sub 2, and there's no interaction between these variables in terms of predicting the outcome variable. So here's a situation in which there is a main effect or a simple effect of predictor variable x sub 1 on outcome variable y. So as you have higher levels of variable x sub 1, you have higher levels of outcome variable y. However, there's no effect of predictor variable x sub 2. It doesn't matter if you're at level 1 or at level 2 of that particular variable in terms of predicting your level of outcome variable y. And there's no interaction between these two variables. Quite literally, the slopes of these two lines are identical. Again, really, they should be entirely superimposed over each other, but there's no difference in their slopes or their intercepts. Here's a situation in which there is no main effect or no simple effect of predictor variable x sub 1 on outcome variable y. However, there is a main effect or simple effect of predictor variable x sub 2, the variable which we're kind of treating as our moderator, at least the way we're framing this whole presentation. Here, it does make a difference. If you're at level 2 of variable x sub 2, you have a higher level of the outcome variable y than if you're at level 1 of variable x sub 2. But there's no interaction. Again, those slopes are identical to one another. That is, they're identically 0 to one another. There's no interaction between predictor variable x sub 1 and x sub 2. Now let's look at some situations in which there are interactions between predictor variable x sub 1 and predictor variable x sub 2 on the outcome variable y. There are just a couple examples here. And right away you can notice that in these examples the slopes of these lines are not the same. These lines are not parallel to each other, which is an immediate way of seeing that there's some sort of an interaction. If we wanted to characterize these in terms of more familiar language, we might say something like, well, the variable x sub 2 enhances the effect of predictor variable x sub 1 on outcome variable y. What we might be suggesting here is, well, at a low level of predictor variable x sub 2, at the low level of this moderating variable, there's no real relationship between predictor variable x sub 1 and outcome variable y. However, at a high level of predictor variable x sub 2, the high level of this moderator, level 2, there is this relationship, and it's strong and positive. Again, you wouldn't have to use this language, but you sometimes see when you read result sections or you scan over papers or even abstracts, you'll see people describe these kind of enhancement effects, and often what they're referring to is a significant interaction that looks like this. Likewise, you sometimes see language that uses the word buffers. You might say, well, predictor variable x sub 2, this moderating variable, it buffers the effect of x sub 1 on outcome variable y, such that, generally speaking, if you have a high level of variable x sub 2, if you're at level 2, whatever that is, there's really no relationship between the predictor variable x sub 1 and the outcome variable y. But at lower levels of variable x sub 2, there is a relationship. Higher levels of x sub 2 buffer that relationship, kind of erase it. Those are just two examples. Again, you wouldn't have to use this language, but you sometimes see it. Now, there are other ways in which our two variables could interact. Here's kind of a classic that you see sometimes in literature, or at least you like to see in literature, because it illustrates kind of a neat, what's called a crossover effect. The relationship between predictor variable x sub 1 and outcome variable y is very different at our two levels of our outcome variable x sub 2. It's positive if you're at a high level of x sub 2, and it is negative if you're at a low level of x sub 2. And it's called a crossover because the slopes of those two lines one is positive and one is negative, so necessarily they somewhere on the in the sort of plane, somewhere in that plane will cross over each other, make a kind of an X shape. And now you don't always see this in the literature, but this is kind of classic in the sense that I think for a long period of time, researchers liked to see this because it suggested a really strong interaction between our two variables, x sub 1 and x sub 2. It really matters what level of x sub 2 you're at if you want to describe the relationship between x sub 1 and y, because there's a crossover interaction. Now, to be clear, in some cases, you can kind of talk about the main effect of a predictor variable, in this case x sub 1, even if there's an interaction. So imagine we have this situation here, what I've previously described as kind of like an enhancement type interaction. You could kind of say, well, what's the average effect of x sub 1 on outcome variable y? Yes, it depends on the level of x sub 2, such that if you're at level 1 of x sub 2, there's no relationship. If you're at level 2, there's a strong positive relationship. You can sometimes try to characterize like an average effect. It depends, of course, a lot on what these variables are, and here I'm just presenting them very abstractly. You sometimes see people, or you will read people in their results sections still try and talk about a main effect or a simple effect of their predictor variable, even when even when there's an interaction with a moderating variable. You can also kind of talk about the simple effect of x sub 2 on outcome variable y. So you're essentially kind of like reversing these variables. Here I've done just rearranged which variable is on the x-axis and which variable is used as the moderator. And you can kind of characterize, well, what's sort of the average effect that you get for outcome variable x sub 2 on y, on predictor variable x sub 2 on outcome variable y. Again, you can kind of do this. But in more extreme cases, like in our crossover, which is really the most extreme type of interaction, at least involving two predictor variables, it becomes essentially impossible to talk about the main effect or the simple effect of any one predictor variable on the outcome variable, because it depends entirely on what level of the other predictor variable you're at, or what's the average here. And so it's unclear. The important point that I'm trying to make, and I guess I've made it before, is that when an interaction is in the model, it's difficult to discuss the effect of any one predictor variable in isolation, or in terms of like its simple effect or its main effect. Sometimes people do this, but sometimes people are wrong. And in essence, as maybe you saw in those previous examples, the stronger the interaction is, up to a full crossover, the harder it is to discuss the nature of those simple effects or those main effects. The other bit of advice, or the other important point to make here, is that you should always graph interactions, at least when you can. It really helps, I think, to visualize and ultimately to characterize the nature of that interaction. So if we go back to our example that we're working with here, we might say, well, the effect of negative body image on eating disorder symptoms is moderated by self-esteem. That's what we saw when we did that comparison of models using SPSS as output. But we might still ask, well, what's the nature of that interaction? What's it look like? Or more generally speaking, what does it mean? Well, here's where things can start to get a little bit complicated. And in this lecture and in the following lecture, or even 2 lectures, I think, I'll be talking about different options you have for interpreting an interaction. And by interpreting, what I mean is expressing pictographically and expressing in language, in your writing and in your speaking, what an interaction means, or how an interaction plays out, if you will. One option you have is to, if possible, graph the interaction. That's kind of what I was using before in my little kind of abstract examples. So you can literally see what the interaction looks like. Another option you have is to express the model for the interaction. That is, do a little bit of algebra to kind of explain or express what the model coefficients, what those little unstandardized regression coefficients, the B's, what they actually mean. And the third option is to perform what's sometimes called a simple slopes analysis. So if the effect of a predictor variable x sub 1 on the outcome variable y varies across levels of the other predictor variable, across levels of the moderator, then we find the levels of that moderator where the effect is significant and levels where it is not significant. Kind of where is the slope or where is that plane warping? Where is that effect shifting from non-significant to significant? That's in sort of vague terms, I suppose, a simple slopes type analysis. And we'll go through some different ways that you can do that in, if not this lecture, in the next one. For the time being, let's focus on those first 2 steps, though, the graphing and the expressing the interaction. Now, graphing an interaction can be tricky to do when our moderator is continuous. In previous examples that I've used, especially my little abstracted examples, I kind of made it easy for myself because my moderator variable was categorical and had only 2 levels. So it was very easy to draw a line for level 1 of our moderator variable x sub 2 and draw another line, make another model for level 2 of the moderator variable. That's easy. And sometimes we do have a moderating variable which has a natural categorical metric, again, like we might use gender or class in college, sophomore, junior, senior, freshman, sophomore, junior, senior, or something like that, treated with antidepressant medications versus not treated with antidepressant medications. Sometimes our moderating term is nice and categorical, and that makes it pretty easy to do the graphing. Sometimes our moderating variable is continuous, like in this example here, where our moderating variable that we're using is is self-esteem. So that's not something which naturally has a high group and a low group. It's more thought of as a construct which occurs across a continuum of values. Nonetheless, we could treat a continuous variable like it was categorical, at least for the purpose of graphing, by forming low and high groups. And there are different ways we could do this. One would be to perform a median split, that is, to divide our sample up in terms of their level of the moderating variable and put the people in the highest 50% of the sample on that variable in one group, call them high self-esteem, but everyone else in the other group call them low self-esteem. It would be splitting the sample at the median on the variable self-esteem, the median on the variable that's our moderator. We could also do the similar sort of thing by picking out some of the folks who are really high on self-esteem. Maybe they're one standard deviation above the mean, and call them the high group. And pick out another group of folks who are one standard deviation below the mean and call them the low group. That example would involve necessarily excluding temporarily, and for the purpose of graphing, some of our data, the people who fall in that kind of middle portion, but we could do that if we wanted to. Now, this is relatively easy to do in SPSS syntax. It's not really that hard to do it manually, that is, to just create a variable in the data frame of SPSS and just assign values to it kind of by hand, by typing them in. Here, just to follow along with what I've done, I've made a little bit of syntax here, and in the upper portion, it's well, actually, I think in both groups what we're doing is dividing people based on their medians. The upper portion here is the median on self-esteem. So I'm saying, if self-esteem is greater than 3.5, is less than 3.5, then the person's value in a new variable that's called cell group, SELGRP, is going to be 0. And if it's greater than 3.5, then the value that the person has on that new variable is 1. And that variable has a particular format. It's got 1 digit and no decimal places. That's what that formats command is. And I've also given a label just to remind myself what it means. I've given value labels to remind myself that 0 means low self-esteem and 1 means high self-esteem. The important part of that syntax is just those two if statements. You could pretty much, I think, run it without those, and execute just runs the command at the end. The bottom portion of the syntax, I'm just doing the same thing with negative body image. In negative body image, the median is 8.5, so I'm kind of doing the same thing, splitting the sample by their median on negative body image, and just to create low and high groups that way. Now, for the purpose of our analysis, I think initially at least, I'm really using self-esteem as the moderator, so I'm creating groups on that moderator. This negative body image bit at the bottom is just to show that you could do the same thing with the other variable if you wanted to treat negative body image as the moderator and self-esteem as kind of the main predictor variable. It's up to you. Anyway, once I've created this new variable, this self-esteem group variable that's categorical, it's got a high and a low value, a level 1 and a level 2, if you will, I can go into SPSS chart builder and I can use scatter plot, and I can now use the scatter plot that allows for grouped scatter plot. That's the sort of second option in our little workspace there. I've kind of clicked it and dragged it into the upper portion of the dialog box. I'm putting negative body image on the x-axis because it's my main predictor variable. I'm putting eating disorder symptoms on the y-axis because it's my outcome variable. I'm putting that new group variable that I made, self-esteem group, up into the set color region. And what that's going to do is it's going to color all the dots in my scatter plot as a function of which group the person who owns that dot is in. Now, if that makes sense to you, good. If it doesn't, just follow along and hit OK, and you'll get a graph that looks a little bit like the following. So here's a graph. All I've done here is I've clicked on it to open up the chart editor in the output screen, and I've clicked on each, sort of clicked on the green dots, and then I click the little button that allows you to add slope lines to the dots. And what SPSS will do is it will naturally kind of put two lines in, one for that high group, which is the green folks, and one for the low group, that's the blue folks. And it will also add in our little regression coefficients for our model, and you can kind of see that, yeah, the slope for these two models is quite different. And if you want to step back for a second and think about it, you might say, well, what this kind of suggests to us is that there is some relationship between negative body image and eating disorder symptoms. The more you dislike your body, the more likely you may be to have eating disorder symptoms. But that relationship is a lot stronger if you have low self-esteem. If you have high self-esteem, it exists maybe, but it's not quite so strong. That's sort of the gist or of the interpretation that we could make by looking at this graph. So again, it looks like negative body image is predictive when self-esteem is low, but not, or maybe not quite so much when self-esteem is high. That's the nature of that interaction. Can we test that precisely? Well, we can by running two regressions for each, I should say running a regression, one for each of our two separate groups. So if you wanted to do this, you could pretty easily in SPSS use data split files and then split the file on that new self-esteem group. So this is a command or Windows-based command here that will take our data and for the purpose of all analyses divide the data up any way we like. In this case what we want it to do is compare groups. You can see I've clicked the little button for compare groups based on self-esteem group. So I dragged my self-esteem group variable into that little workspace there and I hit OK. If you look really closely at the bottom right of your screen, you'll probably see a little command when you get back to the data frame that says split file is on, just reminding you that you have a split file command run on your data set. And now what you do is just run a simple regression, predicting predicting eating disorder symptoms from negative body image. Now we're not including self-esteem or the interaction because again at this point we've divided our data set into two groups. Although it looks like there's one data set, and in a sense there of course is, really SPSS is acting as if there's two data sets now, one for the high self-esteem people, one for the low self-esteem people. And if you clicked on the button previously that says compare groups, the output will be arranged conveniently in this kind of layered format. The output's essentially the same either way you do it, but this is just makes it nice to kind of eyeball the analyses. And you can see here that for the low self-esteem folks, there is a significant relationship between negative body image and eating disorder symptoms. You can see that in the ANOVA table. That is statistically significant. So an augmented model including negative body image is predictive of or is a better fit for the data than a compact model not including that predictor variable if you're in the low self-esteem group, but it's not if you're in the high self-esteem group. You can also look up at the model summary and see that there's obviously a difference in R squared. We're explaining maybe 56% of the variance in people's eating disorder symptoms in terms of their negative body image if they're in the low self-esteem group, but barely 4-5-6% if they're in the high self-esteem group. Now, to be clear, this is fake data that I cooked up, so we see a pretty strong interaction here. A really nice illustration of how this would work. It's certainly conceivable that we might see a significant effect in both groups. That wouldn't mean that there is no interaction. It's just here I've kind of cooked up the data so that you see this really strong interaction where it totally works. The effect of negative body image kind of totally works for one group and doesn't apparently work very much for the other group. So again, if we slide down and look at some of the other output, we could see our regression coefficients here with their little t-tests, and we could interpret them as such. We could say, well, negative body image is really only predictive of eating disorder symptoms if you're in the low self-esteem group. If you're not in the low self-esteem group, then negative body image is not predictive. You can see that the significance test for the regression coefficient of negative body image is not significant. If you're in the high self-esteem group, it is significant if you're in the low self-esteem group. And I've created some confidence intervals for those regression coefficients as well. You kind of had to cut the table up to fit it on the screen. You can see in the case of the high self-esteem group, the confidence interval for the slope describing relationship between negative body image and eating disorder symptoms, that confidence interval spans across 0. It goes from negative 0.24 up to positive 1.2 8. Now that confidence interval overlaps with 0, meaning that we're not really sure whether the real in the population slope for that relationship is any different than 0, at least not at this level of confidence, at 95% confidence level. So bottom line, as I've said now a few different times in a few different ways, is the interaction works such that there is a relationship between negative body image and eating disorder symptoms among the low self-esteem people, but not among the high self-esteem people. Now again, I've made this data deliberately to be a bit of an easy interpretation, and you might well ask, well, what if the results weren't so obvious? What if it was the case that the model was significant for both groups? More specifically, in this case, if negative body image was predictive of eating disorder symptoms in both groups, would this be a problem? Well, it's not really a problem. A significant interaction term tells us that there's a difference between the slopes of these two models. They could still both individually be significantly different from 0 and also be significantly different from each other. If by using a simple median split we didn't see as obvious a picture, literally, as we saw in this case, then we could, if we wanted to, come up with other groups. Like we could come up with like the low group versus the high group and kind of graph them to see if the interaction is more obvious there. That wouldn't be a bad thing to do exactly. It would help us maybe characterize the nature of that interaction. Now, I just said it wouldn't be a bad thing to do, and the truth though is that dichotomizing continuous variables, which we've done here, we've taken a continuous variable, self-esteem, and broken it up into groups, treated it as if it was a group, a categorical variable, is a bad thing to do, or at least that's something that a statistics teacher of mine used to say. And what he meant, really, is that it can cause problems. People do it. I've done it in papers before, and probably many people have as well, but we have to acknowledge that it can create problems. It can obscure or even confuse significant effects, making it difficult for us to be entirely comfortable with the interpretations that we make. So we should be a little bit cautious about this approach. If we are in a situation where we want to make graphs and our moderating variable is continuous, and so we want to break it into categories for ease of graphing, we can do it, but we should be a little bit cautious and treat our work as a kind of a exploratory analysis, something that we're using for interpretive purposes, but maybe a little bit misleading. To explore this a little bit further, let's think about what happens when you dichotomize a continuous variable. At a very basic level, you reduce variability. Think about it. If you've measured self-esteem on a group of people, 60 people, I think is how many folks are in this data set, most of these people don't have exactly the same value on self-esteem. There's a lot of variability in the scores that people have. We might say, there's a particular variance we could compute by trying to describe sort of the average squared difference between anyone's score on self-esteem and the average for the whole sample. When we break when we break that variable into groups, high self-esteem, low self-esteem, now a lot of people have the same value. Like there are a lot of people, half of all people are in the high group and half of all people are in the low group. So across the whole sample, there's a lot less variability, there's a lot less variance in that variable. Less variance means necessarily and mathematically less covariance. And because our analyses of interactions and of other because the analyses that we're doing depend on covariance, we lose statistical power to detect relationships between our moderator variable or an interaction with our moderating variable and our outcome variable because we've shrunk the variance on that one variable. Now, if that's a lot of me talking and it's a little bit hard to follow, let's see if we can represent this pictographically. So here are two tables. I've used my data in SPSS and I've broken out, these aren't all the cases, but you can see like the first 20 cases in the low self-esteem group and the first 20 cases in the high self-esteem group. These people have different levels of self-esteem and there's some variability between them. Not a lot. You can see almost everyone in the low group has either 1 or 2 on self-esteem, although there would be more people there if I had more space to show it on the screen. But when we put them all in the same group, they now have exactly the same value. That value is 0 or what 0 is coded as is labeled low in my analysis. Likewise, if we look at the high self-esteem people, almost everyone has either 5 or 6, although there would be more numbers and more variability if I could show more data on the screen. But when we form a group based on self-esteem using a median split, now all those folks have the same value. They have a value of 1, which is labeled as high. So I've literally reduced the variability. I've reduced the variance, which is just variability with respect to a mean. Less variance means less ability to have covariance with other variables, including with the other predictor variable and with the outcome variable, so less power to detect significant effects. So you can see that quite literally here. If I form on the left here, this is just the variance for the entire sample. I'm using all 60 cases, and the variance or the standard deviation, I guess I've computed here, happens to be 1.7. And if you look at the standard deviation for each of the groups, that's if I form groups, you can see that on the right, it's 0.83. So less standard deviation, less variance, less covariance, or less of a possibility of covariance with other variables. Also, splitting a file like we've done here for the purpose of running those little regressions reduces the sample size. So when I ran those little follow-up regressions after making the graph, I was like, oh, let's run the regression for the high group. Let's run the regression for the low group. I was running those regressions based on samples which are now half as big as they previously were. And smaller samples means less statistical power, and the test statistics that we have are just going to be less reliable. All right, so maybe you're sick of me talking, or maybe you agree with me, and at this point you're saying, okay, this is bad. But actually it can get worse. Dichotomizing variables actually increases variability right at the point where the cut score for group membership occurs. That means that at the point at which we've divided people into high self-esteem and low self-esteem, right at that boundary, the people who fall into the high group are not really all that different from the people who fall into the low group. They have pretty much similar values on our variable, in this case self-esteem, but we're treating them like they're very different. We're saying to one of those people, hey, you're a high self-esteem person. We're saying to another person, oh, you're low self-esteem, and the actual difference might not be very great. You can actually see that here. I've just kind of ordered up the data by self-esteem, and you can see here at the point at which you're in the low self-esteem group and the point at which you're in the high self-esteem group, your actual level of self-esteem may not be that different. Now in this case, I've made up this data, but the principle would apply with actual real data. At the boundary between our two groups, there's actually not that much variability between the people, or not much of a difference, I guess I should say, between people who fall into the low group and people who fall into the high group, and that can actually lead us to see strange patterns of results in our analyses. Consider this. What if we are running the analysis kind of the other way? We're basically doing it like we did before, except this time we're predicting eating disorder symptoms from self-esteem, and we're using negative body image as our moderating variable. Here, if we were to kind of form up groups using negative body image, kind of like I did before, we see in our analysis that the slopes are different. There is an interaction, but they don't seem very, very different. If we were to run follow-up regressions on the high and low negative body image groups, we'd find that both of them are statistically significant, and we might not really be able to offer much of an interpretation of the difference. There is a negative relationship between self-esteem and eating disorder symptoms, and it's true in the low negative body image group and the high negative body image group. Again, we might say, well, low self-esteem is predictive of eating disorder symptoms in both of these groups. Now, that's not a problem. That's not like per se a bad thing, but it's just an example of how that limited variability that occurs when we dichotomize a moderating variable can sometimes lead us to draw very different conclusions. Like, imagine that we hadn't essentially done the analysis both ways. Imagine that our first step was to run these analyses using negative body image as our moderator. We might say, there's some interaction there, but it's not very strong or very interesting, full stop. Whereas if we done the analysis as we did the first time around, which is we treated self-esteem as the moderator, we might have said, well, look, there's this pretty strong and kind of interesting looking interaction, full stop. Same data, two different interpretations, maybe even two different result sections that we would write for our paper, based at least in part on this, let's say, somewhat arbitrary choice as to which variable got to be the moderator, and this somewhat problematic decision to categorize or dichotomize, which is to say to make a two-group category system based on a continuous variable, either self-esteem or negative body image. So caution, dichotomizing continuous variables is bad. Well, it's maybe not bad, but it can cause problems. Our previous analysis wasn't entirely wrong, but it was potentially misleading, or at least it got us to a very different place than our initial analysis. In some analyses, the problem could be even worse, where we might see, we might miss an interaction or miss a significant effect because of low power, or we might be somewhat confused in the interpretations that we make. So again, you can graph analyses as we've done here to kind of gosh, I'm stumbling here a little bit. You can use graphing as a tool to characterize, that's the word I was looking for, interactions. But if you do that, sometimes you'll be in this unfortunate position of having to categorize even dichotomize continuous moderating variables, and if you do that, you can sometimes get into a position where you have a hard time being entirely comfortable with the results of your graphing and the results of your analyses. With that in mind, let's move on to consider another approach that we might take for characterizing an interaction. Okay, so let's go back to our original analysis. That is the analysis in which we used negative body image as our main predictor variable and eating disorder symptoms as our outcome variable, and we thought about using self-esteem as a moderating variable. Now recall that we found a significant interaction between our predictor variable and our moderating variable, and what we want to do is express the nature of that interaction. Or characterize the nature of that interaction. One approach would be to do some graphing, and this sometimes can be really valuable. I often suggest it as like the first step, but there are sometimes real limitations to how much we can do with graphing. Sometimes the graphs aren't entirely clear. Sometimes we have to categorize continuous variables, and that's problematic. What are the other options we have for characterizing an interaction? Well, the next thing that I often do is I try to express the model for the interaction, and by that I mean I want to explain what the model coefficients actually mean. Now this process may seem like it's tricky the first time you see it done, but once you get the hang of it, it's really easy, and it's also pretty valuable to do, or it's useful to do, I should say. Anyway, the first step of the process is to just get those unstandardized regression coefficients, those little betas, for the original regression. So here I'm just looking at my output. I'm looking at model 2, that's the version of the augmented model that includes both the predictor variables and the interaction. I'm looking at that column for unstandardized regression coefficients on the left there. Now, using the information from that output, I'm going to go ahead and write out the model. That is, I'm going to write out the regression equation. I'm just substituting in the values for b sub 0, b sub 1, b sub 2, and b sub 3 into my equation, as you can see at the top here. And then just for the ease of kind of interpretation, I'm going ahead and substituting the names for the variables in for y's and x's and so on. And so you can see there my equation, eating disorder symptoms equals 34.5 minus 0.9 times self-esteem plus 2.2 times negative body image minus 0.3 times self-esteem times negative body image. That's just my basic regression equation. I've written out the model. The interesting thing now is I'm going to rearrange those terms slightly so as to express them, same information, just with these parentheses as you can see at the bottom. I haven't done anything other than slap a few parentheses up there to kind of rearrange the terms. Now what I've done here is I've written out the model in such a way as to express the simple relationship between eating disorder symptoms and negative body image. And I can read the model this way. I can read that first parenthetical grouping as the intercept term and the second parenthetical grouping as the slope term. And the value in doing this is it just highlights the ways in which self-esteem changes the relationship between negative body image and eating disorder symptoms. It highlights the way in which the slope goes up or down, and which the intercept goes up and down at different levels of self-esteem. So to be a little bit more precise than that, we can say, look, the intercept for the model for the eating disorder negative body image relationship is 34.5 when self-esteem is 0. So if you've plugged in values for 0, you could solve it out and that's what you'd get. That intercept changes. It goes down by 0.9 for every unit that self-esteem goes up. So every amount that your self-esteem goes, every time self-esteem goes up by 1, that intercept goes down by almost 1. Moving on, you can see that 2.2 is the slope for the eating disorder negative body image relationship when self-esteem is 0. But as self-esteem changes, so does that slope. It goes down by 0.3 for every unit that self-esteem goes up by 1. And what's really cool about this is you can just plug in different values for self-esteem and observe how the slope and the intercept for the model that is of the simple negative body image eating disorder relationship, how it changes. Now, by the way, I'm putting simple in quotes here to suggest that the relationship really isn't simple. There's an interaction here. It depends on the level of self-esteem. But what we're trying to do is kind of give the reader, or give you as the data analyst, a sense of how the intercept and the slope are shifting at different levels of self-esteem. Specifically, as self-esteem goes up, we can see that the intercept for the model drops down and the slope for the model becomes more shallow. So far we've considered two options for interpreting or for characterizing an interaction. One is to graph it, which kind of gets at the basic question of, what's the interaction what does it look like? And the other is to express the model for the interaction. That is, explain what the model coefficients mean, specifically allowing us to understand how the relationship between one predictor variable and the outcome variable changes at different levels of the other predictor variable. That is, at the other levels of the moderator variable. Can these methods work together? Usually they can. Graphing is, of course, visually more appealing, but expressing the model is more precise. Although it's interesting to note that sometimes these two can be slightly contradictory. So if we take a look at the graph that we made by dichotomizing our moderator, self-esteem, into a self-esteem group that's either high or low. And if we look really closely at the left side of the graph, we can see what kind of a weird finding with regards to the intercept. It kind of looks like if we move from people with relatively low self-esteem in blue to people with relatively high self-esteem in green, the intercept actually goes up a little bit, which is in contrast or in contradiction to what we saw when we expressed the model. Now, why is that happening? Well, it's happening just because these lines on this graph are made with respect to just portions of our data. So the line in blue is a line that is fit to only the blue data points, and the line in green is the line that's fit to only the green data points. So in a sense, we're making lines to represent simple slopes using only portions of our data, and that fact makes the lines slightly incorrect with respect to the entire data set. We can see an even more extreme version of this if we try to make many different self-esteem groups. So instead of just having a high group and a low group, what if we had like a low, high, medium, etc., etc. I just kind of made one group for every possible level of self-esteem. And here the lines look like they go all over the place. As we go from people with low self-esteem in blue to people with high self-esteem in red, there's sort of this impression that the line is becoming more shallow and the intercept's dropping, but it's kind of chaos all over the place. And so basically what this illustrates, hopefully, is a kind of a really extreme case where if we form lots and lots of groups and cut up our data into smaller and smaller subgroups, then the lines that we get really make less and less sense with respect to the whole data set. To put this another way, we can say, well, why is there this inconsistency? The graphs that we're making, the lines for those graphs, are made from subgroupings, and those lines will fit their subgroup data somewhat differently than they fit the whole data, or that is to say, the full data set. Now, is this a problem? Not necessarily. It's just something we really need to keep in mind when we use this kind of quick and dirty approach to graphing, when we form subgroups from a continuous moderator variable and then quickly graph it that way. It can be useful for us to get a general sense of what an interaction looks like, but we should always keep in mind that it's probably going to have at least some amount of imperfection in it. It's always going to be more precise to express the simple model for the interaction as I've shown in previous slides. And interestingly, we can actually combine these approaches. That is to say, we can combine the precision of expressing the model with the visual appeal of making a graph. And this combined approach, again, is just to express the model for the interaction and then make graphs that are based on predicted scores, for instance, for people who are 1 standard deviation above the mean and people who are 1 standard deviation below the mean. So we can make our models, find predicted scores, and then graph those scores and make lines for just them, and that will use the full data set, which gives us the precision, but also gives us the ability to kind of compare high groups and low groups and so on and so on. It's a nice way that I think gives us the best of both worlds. So how would this work? Well, we could begin by expressing the model for the interaction and then use values for self-esteem that are 1 standard deviation below the mean. So in this case, here's my model, just like I expressed it in previous slides. And now I'm substituting in the value 1.8 for self-esteem, because 1.8 happens to be the value for self-esteem that is 1 standard deviation below the mean. So if I just plug in the numbers, that is plug in 1.8 into the equation and then solve it, I get an equation that looks like this. This is the simple slope for the relationship between negative body image and eating disorder symptoms for people who are 1 standard deviation below the mean in terms of the moderating variable that is self-esteem. And we can do the same thing for people who are 1 standard deviation above the mean, again taking that same equation, substituting in a different value. 5.2 happens to be the mean for self-esteem plus 1 standard deviation. Of course, you can find this pretty easily using descriptive statistics. I take that value, 5.2, I plug it in to my model, I solve it, I do the math, and here's my simple slope for the relationship between negative body image and eating disorder symptoms for people who are 1 standard deviation above the mean. Now, if I put these together, I've got a kind of a nice, I can make a nice table to reflect how the slope and the intercept change when I compare relatively extreme levels of self-esteem, like people who are rather high in self-esteem as compared to people who are rather low in self-esteem. And it's actually pretty easy to graph these lines on my scatter plot. Now let's see how this would work in Excel. What I'm going to try and do is make some different predicted values for each of the people in my data set. And if you're looking really closely, you might notice that I've sorted the data set by self-esteem ascending. So we're starting with the people who have the lowest self-esteem and going up. That's not important. That just happens to be the way I had sorted the data at about the time I took this picture. Anyway, what I'm going to do for each person is create different predicted values. I'm using the same basic approach for all of them. I'm saying that predicted value is just the b sub 0, that's the regression coefficient for the intercept, plus b sub 1, that's the regression coefficient for the slope of self-esteem times self-esteem, plus b sub 2, regression coefficient for the slope of negative body image times negative body image, plus b sub 3, that's the regression coefficient for the slope of the interaction term times the interaction term. That's the basic kind of formula that I'm using. And so you can see in the case of the straight old regular predicted value, I'm taking the information for each person, in this case the person in row number 2, and I'm plugging in their values. Those $B, $68, $B, $69, those are just where those coefficients are located, and they're at the bottom of the spreadsheet. You can't see them on this image. But what you can see is for person number in row number 2, I'm taking the intercept plus the regression coefficient for self-esteem times cell C2, which for person in row 2, that's the cell that has his or her self-esteem value, and plus the regression coefficient for negative body image times D2, that's the cell for that particular person where that person's negative body image is, and so on, and all the way down the row, or I'm sorry, down the column, I'd be doing the same thing except with each successive row of data. So it would be sort of C2, D2, E2, C3, D3, E3, and so on and so on. That's the basic approach that you would take when calculating the predicted values for each person. What's new, or what I'm doing a little bit differently now, is I'm going to substitute in values for those for self-esteem that are 1 standard deviation below the mean and 1 standard deviation above the mean. So for instance, for the person in row number 2, I'm going to use that same equation, but this time instead of allowing the value for what that person's self-esteem is, which is located in cell C2, I'm going to plug in that value 1.8. That's 1 standard deviation below the mean. It's like saying, what if that person, whoever he or she is in row 2, what if her self-esteem, his self-esteem was 1.8 instead of the value that it actually is? That would give me kind of like a low prediction for that person. Like, what if their self-esteem was 1 standard deviation below the mean? Or for that matter, what if their self-esteem was 1 standard deviation above the mean, which is happens to be that value of 5.2. So I'm just using these equations to create what I'm calling low predictions and high predictions for each person, acting as if their self-esteem was either 1 standard deviation below the mean or 1 standard deviation above the mean. Then I'm making a simple scatter plot between negative body image and eating disorder symptoms. Really should have labeled the axes on this scatter plot. I hate it when researchers don't label their axes, but oh well, my mistake. I'm making a simple scatter plot, and then I'm adding custom trend lines, and I'm not showing you how to do this, but poke around in the menus for Excel. It's not that difficult to find the area where you can add a custom trend line, and the custom trend line is just those columns for the low prediction and the high prediction, and they give us these nice simple slopes that look a little bit like this. If you want to make this essentially the same graph in SPSS, it's actually really easy. You start again by making a simple scatter plot that represents the relationship between negative body image and eating disorder symptoms, and then you click on the button I'm indicating up there at the top to add what SPSS calls a reference line, and this is going to be a custom reference line based on the equations that we found earlier for low and high self-esteem. That is 1 standard deviation below the mean on self-esteem and 1 standard deviation above. You can see here I've typed in the equation for the 1 standard deviation above there, and I just hit apply, and then I repeat the process for the other line, and I get something that looks rather neat, a nice little graph kind of like this, and I can use some text boxes to add some labels here to indicate what those are, and I get, I think, a really nice looking graph that gives you a sense of how the relationship between negative body image and eating disorder symptoms changes across different levels of self-esteem. So let's do a quick review. We've been looking at different options for interpreting an interaction. These include, for instance, just making a kind of a quick and dirty graph where we take our moderator variable, which is often, especially in regression type analyses, going to be a continuous variable, and we break it up into groups. We maybe dichotomize it into a high and low group or something like that. This is a quick approach because it's pretty easy to do in SPSS. It's kind of a dirty approach in the sense that it sometimes leads us to incorrect conclusions about the nature of the interaction. We're necessarily chopping up our data, and that can create some interpretive problems. Another approach is to express the model for the interaction, by which I mean express the slope and the intercept of the simple relationship between the predictor variable and the outcome variable as those two elements, the slope and the intercept, change for different levels of the other predictor variable, the moderator. This is a little bit more challenging to do, at least in the sense that it involves a little bit of algebra, but it's not really all that hard once you get the hang of it. And it is more precise. It is perfectly precise, at least in terms of describing the interaction in your data. You can even do what I call a simple slopes analysis. Not just me, I think many teachers and authors would call a simple slopes analysis, essentially by combining these two approaches. Using the more precise method of expressing the model to create a table of different values for slopes and intercepts, and then maybe even graphing them to kind of give you the visual appeal of a graph. And you kind of get the best of both worlds, the visual appeal of the graph and the precision of the properly expressed model. Now, simple slopes analysis is even more than that, or there's more that we can do by way of simple slopes analysis, and I'll actually get to that in my next lecture. I'll introduce a plugin that you can use for SPSS to give you some more information and more analyses of simple slopes. And also in my next lecture, I'll introduce mediation analysis, which is this other kind of fascinating area of interactive models. So I'll get to that soon, but this has been a long lecture. Again, we're clocking in at a little bit over an hour, so if you've made it this far, as I always say, thanks for your attention. I really do appreciate it. If you have some time, sit down, have a cup of tea, a cup of coffee, whatever is your pleasure, and think about what you've learned. Hopefully this stuff makes sense to you. If it does, great. Try it, practice it in SPSS to see if you can get the same results that I got. Practice it in Excel if you really want to challenge yourself. If you're having trouble and you're in my class, obviously just email me or talk to me in person or post on Blackboard. If you're just watching these videos on YouTube, then wow, you're a special person who's really dedicated yourself to learning about statistics. You have my respect. Leave a comment for me and I'll do my best to notice those. I look almost every day, and I'll do my best to answer those comments or those questions you leave. All right, thanks very much. Bye-bye.